Welcome to Summarize Science. Imagine teaching a robot to make you breakfast, not by writing a single line of code, but just by letting it watch you for a few minutes. This has long been a dream of AI researchers, but teaching robots to have human-like dexterity is incredibly difficult. A new research paper presents a framework called AINA, which takes a huge leap towards making this dream a reality. The core idea is simple but powerful. A person wears a pair of advanced smart glasses, in this case, the Aria Gen 2, and just goes about performing a task. As you can see in this diagram, the workflow starts with collecting data in the wild, which means anywhere, with any background. This data is then used to train a robot policy, which is essentially the robot's brain for that specific task. These aren't just regular camera glasses, they are packed with sensors that can accurately track the 3D position of the user's hands and head. This is the secret ingredient, as it provides rich 3D information about the movement, not just a flat 2D video. To make sure the robot understands its own workspace, the user also performs one quick, single demonstration in front of the robot. This one demonstration acts as an anchor, translating all the in-the-wild knowledge into the robot's specific environment. Here's where it gets really clever. The AI doesn't learn from raw images, which can be confusing due to different lighting, colors, or background clutter. Instead, it learns from a 3D point cloud, basically a minimalist connect the dots of the object and the person's fingertips. By focusing only on these essential 3D points, the robot learns the fundamental geometry of the task, making the skill much more generalizable. So, does it work? The team tested AINA on a robot with a multi-fingered hand across 9 different everyday tasks. These included tasks like pressing a toaster lever, opening a drawer, wiping a surface, and even pouring from a cup. As you can see from these rollouts, the robot successfully learned to perform these complex motions with a high success rate, all from an average of just 15 minutes of human video. The researchers showed that their specific recipe was crucial for this success. Policies trained only on data from the robot's specific scene failed to generalize to new positions. And policies trained only on the in-the-wild data struggled to be precise in the robot's environment. It was the combination of both, co-training with diverse wild data anchored by one in-scene demo, that enabled this robust performance. The system even showed it could generalize to new situations it had never seen before. For example, it could still perform tasks when the workspace height was changed, requiring just one new quick demo at the new height to re-anchor itself. It could also generalize to new objects with similar shapes, like using a board eraser instead of a sponge, just by being given a new text prompt. So, let's recap the breakthroughs here. First, this work shows that robots can learn dexterous manipulation from a very small amount of human demonstration data, without needing any direct robot programming or simulation. Second, using smart glasses that capture 3D hand motion is a game-changer for bridging the gap between how humans and robots perceive the world. And third, learning from 3D points instead of 2D pixels makes the learned skill robust to visual distractions. While there are still limitations, like the system not understanding force, this is a major step forward. This could pave the way for a future where robots can be easily taught new skills in our homes, factories, and assistive care settings, simply by watching us. The most profound technologies are the ones that disappear into our lives, and this work brings us one step closer to robots that can seamlessly learn to help with our daily tasks. Thanks for watching Summarize Science.